Welcome back to another video on my channel. Today we will be talking about most of the logarithmic and exponential integrals. Now, the integrals that we will not be talking about, the reason for that is because the techniques required to prove those integrals are a little too advanced for what we are doing right now, and we have not covered those techniques yet. But when we cover those techniques yet, I will for sure provide a proof for those integrals and cover those integrals. So, without further ado, let's move on to the actual video of the integrals that I will provide the proof for and two quick examples. So, let's go. What we have over here is we have logarithmic and exponential integrals. The first integral that we will be talking about is the integral of 1 by x dx, or this can also be written as dx by x. Now this integral is equal to the natural logarithm of x plus c, and as you can see I have a absolute value for x because logarithm cannot take any values lower than 0, and even 0 it's not allowed to have. And the reason also is because 1 by x, 1 by 0, dividing by 0 is a big no-no, and that is not allowed. So let's go to actually proving this. Now what we're going to start with is y is equal to the natural logarithm of x. And the reason is this: if I can prove that dy by dx is equal to 1 by x, that means by the exact opposite process and by the fundamental theorem of calculus, where integration is the opposite of differentiation, I can prove that 1 by x dx integral is ln x plus c by simply taking the opposite. So let's get started on proving this. Now that we have y is equal to ln x, what we can do is we can have e to the power of y is equal to e to the power of ln x, which is x. Now, using implicit differentiation, which is a differentiation technique, we can differentiate both sides. Now, if you don't know what I'm talking about, I assume, since you're learning integrals right now, that you have a knowledge of derivatives, but if you don't, go check out my derivative series where I cover all of this good stuff, and so you can have a better experience overall. So, now that we have that covered and you know if you don't understand where you can go, let's actually differentiate this. So, using implicit differentiation, we get e to the y times dy by dx is equal to just 1. But, as you can see earlier, we have e to the y is equal to x. So, x times dy by dx is equal to 1. So, dy by dx is equal to 1 by x, and now that we know that, the opposite is also true, so we have now proved that that is correct. Now, if you're wondering how the derivative of e to the x is just e to the x, that's also covered in my differentiation series, so you can also go check that out, just as I said earlier. So, now we have the proof of our first integral. Then, let's get into our next integral. What we have over here is we have the integral of e to the x. Now this is just equal to e to the x, and the proof for this is very simple. If we have y is equal to e to the x, that means dy by dx is equal to e to the x, and taking the integral gets us the integral of e to the x is equal to y, which is just e to the x, and then of course our integration constant c that we always need to add. So that's our next one. The third integral that we're going to do is the integral of e to the ax dx. Now this is also a little more complicated, but it is still really relatively simple. So what we can do is, for our proof, we can have y is equal to e to the ax. Now what we can do is we can differentiate both sides. So dy by dx is equal to a times e to the ax by the differentiation techniques, the chain rule. So what we can have after that is, what we can do is we can integrate both sides. So now we know that the integral of a times e to the ax dx is equal to y, or e to the ax. So by our constant rule of integration, we can bring out a, so a times e, the integral of e to the ax, is equal to e to the ax. So we know that this, the integral of e to the ax dx, is equal to e to the ax divided by a, and then of course plus c. So that's how we prove that integral. Now the final integral that we are going to prove for today is going to be the integral of a to the x dx, where a is a constant. So what we start by doing is we start by realizing we can use the change of base formula, or just using a is equal to e to the power of the natural logarithm of a, since they are opposites. Now using this, we get a to the x becomes e to the power of x times the natural logarithm of a dx. Now since we have that constant a, and ln a is a constant, we can use our same integral that we derived right before this to get this integral is equal to e to the x times ln a divided by ln a plus c, and this becomes e to the x times ln a is just a to the x, so a to the x divided by the natural logarithm of a plus c. So that's how that proof works, and that's the final integral that we're going to prove today. So without further ado, let's move on to our examples. Our first example is a relatively simple integral. We have the definite integral from 1 to e of 2 by x dx. So the first thing that we're going to do is we're going to use the constant rule of integration and factor 2 by x dx out of there. Or sorry, not 2 by x, just 2. So 2 now times the integral from 1 to e of dx by x, or 1 by x dx. So this by earlier, this is going to be equal to the natural logarithm of x. Now in definite integrals we don't have c, because c is going to get cancelled out anyways. So now what we can do, what we've covered about doing definite integrals and integrating them, which was covered earlier in our integration series. If you haven't seen that, be sure to check that out. But we plug in e, so 2 times ln of e minus the natural logarithm of 1. Now, the natural logarithm of e is 1, so 2 times 1, and the natural logarithm of 1 is 0. So this becomes 2 times 1, or it's just equal to 2, and that's the answer to our first problem. As you can see, that is a relatively simple integral to evaluate, and while this can get more complicated as we add more and more techniques, this is about what I'm going to show you for now. Now, let's move on to our second example. This example has 5 to the power of x dx. Now this is just a specific form of the integral of a to the x dx, which is a to the x by the natural logarithm of a plus c. So, just plugging that in for that, our formula, we get 5 to the x divided by the natural logarithm of 5 plus c. So, that's really about it for this example. I understand that this example was short, but there's not really much we can do without adding some more techniques, which will be covered in the next video. So, that's really just about it, just to see how it works, how it's put in action. So that's about it. And Thank you so much for watching this video. If you enjoyed this video, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And be sure to comment down below any suggestions, encouragement, or anything positive you have for the channel, as it really helps me out. And even though it's not anything about money, but it really does help me, as it helps me make this channel better for all of you. Thank you so much. See you in the next one, and bye-bye.